And as we see, Amos is now on screen. And with that, I very much welcome you, Amos, to this afternoon session. Just a very brief background. Amos is a musician with a very clear distinction, has produced many, many works, and is currently also still pursuing a PhD at Hebrew University, if I'm correct about that. If not, please correct me. We're looking very much forward to your talk on rapid responses to auditory frequency changes, its magnitude, direction, from brain processing to action. Amos, the floor is yours. You may have to still turn your sound on. I still see that your sound is off.
Can you hear me now?
Now I can hear you. Wonderful.
All right.
Thank you.
Sorry.
No worries.
Okay, so hello to all. My name is Amos Boasson, and I'm both a researcher and a professional musician. As Sonia said, I'm a violist and conductor. And I will present here the last study of my doctoral journey in musicology, which I completed in 2020 at the Hebrew University in Jerusalem, under the supervision of Professor Roni Granot, the former head of the musicology department. And this study was hosted under the auspices of the Edmond and Lily Safra Center for Brain Sciences, known as ELSEC, at the Hebrew University, and specifically at the Human Cognitive Neuroscience Laboratory of Professor Deouell, who is affiliated to both ELSEC and the psychology department at our university. And my colleague gal.vishne assisted me greatly at analysis, so I'd like first to thank Roni, Leon, and Gal for their share in the work. And I also would like to thank deeply Professor Israel Nelken, head of the ELSEC and head of my doctoral committee, for his mentorship and inspiration. My research question concerns human motor reactions in response to auditory frequency change. Perceivers of auditory change in the environment react instantaneously to behaviorally relevant cues. Could this evolved link between auditory input and motor output play a role in music? Could this motor link form a facet of embodied music perception? Motor response to music. One thinks obviously about beats and irresistible groove. But my research focus is on frequency change, the melodic aspect of auditory input. What about this major cornerstone of music and of prosody in speech? Is it too innocent to evoke an immediate motor response? Surely not, because perceiving frequency changes is crucial to behavior. The magnitude, rate, and direction of frequency changes reveal not only immediate past and present, but predict the immediate future as well. So melodic movement should not be a metaphoric expression. But how does auditory frequency change bring about behavior? How to find out about concrete, swift motor responses to frequency change? In previous experiments, we examined the effect of perceiving frequency changes on motor action in a finger tapping task. Isochronous beeps were set in sequences, which presented task-irrelevant increments or decrements in either frequency or intensity. We monitored negative mean asynchrony and muscle action. We found that tapping was modulated right away. On the very next tap following presentation of frequency change, motor action was issued too early. Furthermore, a melodic asymmetry was revealed. Yet more enhanced tap earliness followed melodic rise versus melodic fall. Muscle action following a melodic rise was modulated already at 160 milliseconds after change onset, and melodic fall impacted action significantly later. And lastly, we found diverging response patterns to frequency change versus those to intensity change, suggesting that frequency change's effect was domain-specific. So we had a promising affirmative answer. Frequency change swiftly modulated motor behavior. For the current study, we had two main issues. First, we wanted now to probe motor actions, which are evoked by frequency change rather than modulated by such change. So we opted for reaction time task, RT. We also wish to know more about the processing of the change in the brain, and when and where and how is our evoked motor response issued. This led us to the Human Cognitive Neuroscience Laboratory of Professor Leon Deouell. Here we could monitor participants' brain and brainstem activity while they responded to the stimulus. We tested so far only musicians, 32 top instrumentalist musicians. Our stimulus was a rapid stream of beeps in which frequency shifts occurred. Subjects were required to respond by a button press to any frequency change as fast as possible. The beep rate was dizzy, 8 per second, and jittered. Long beeps and narrow gaps resulted in almost continuous sound. Each frequency change constituted a trial. And these trials occurred very frequently, on average 1 per second, and were strung into preset sequences of different lengths presented in randomized order. As to frequency content, 3 tones were at the core of the design. However, to create equal probability of rise or fall by single or double step, from each of them, 2 more tones were added on either side. The frequency of the midtone, M, was 530.5 Hertz. The unit for frequency steps was 480 cents, what musicians might call an imperfect fourth. And frequency shifts were of single, double, triple, or quadruple units. Interbeep and intertrial intervals and sequence length were randomized, as well as trial type, of course. However, randomization was controlled to achieve equal number of the trial types and to avoid repeated patterns. On the bottom right, we see, On the bottom right, we see the trial types of which the sequences consisted. Solid line types on the left occurred 165 times each, and dashed line types half that amount. The solid lines show that from the 3 central tones, L1, M, and H1, departures were fully balanced as to step size and melodic direction. Importantly, into the mid-tone, arrivals were also balanced, enabling us to have a control test of our parameters without the confound of absolute frequency. We recorded at a high sampling rate of 16 kilohertz to be able to read the brainstem activity. We employed 2 external electrodes as EMG electrodes, recording the flexing muscle of the responding index finger, a muscle which is in the forearm. Another external electrode was placed at the lower neck on the 7th cervical vertebra, a vertical montage to record auditory brainstem. We examined the auditory processing components from wave 5 of the brainstem response up to N100, as well as the frequency following response, FFR. Additional data, namely finger acceleration and reaction time, were acquired in parallel. Since reaction time distribution is ex-Gaussian, it is customary in the RT studies to trim the data. We used the robust adaptive method and trimmed asymmetrically 15% of both tails of that distribution. The responses selected that way were also the ones taken for all other analysis. Our participants were instructed to react as fast as they could to any frequency change, but avoid pressing the button prematurely. This double aim of maximum speed and minimum false starts was stressed also in on-screen feedback at the end of each of the 11 blocks, in which participants could see the mean RT and percent of valid responses they attained during the block. Moreover, bonuses were offered for excelling at both speed and discipline. Though all frequency changes were easy to perceive, very easy to perceive, the task was extremely challenging due to the multi-level randomization of the stimulus, the speedy trial rate, the sensory overload of these jittered filler beeps, and the stress on aiming at both speed and accuracy. So now finally to our results. Reaction times were rapid. The mean reaction time of our 32 participants was 203 milliseconds, especially impressive considering their avoidance of false starts with a mean of 92% valid responses. Also consider that the task was not a simple reaction time task. Our participants had to judge under a buzz of jittered beeps whether a beep's frequency is same or different. Here are results of some extraordinary participants. To examine the effects of magnitude and direction of change on the response latency, we ran several repeated measures ANOVAs. Arrivals into midtone were analyzed by their change magnitude, single step versus bigger steps, and by their melodic direction, rise versus fall. In a separate ANOVA, arrivals by single steps only into the three central tones were analyzed by their melodic direction and by the destination frequency, L1, M, or H1. Then these arrivals were paired anew to reflect motion inward versus outward of the overall frequency range. And finally, arrivals into L2 and H2 were analyzed by change magnitude and destination frequency, which in this comparison is admittedly conflated with melodic direction. We added to all ANOVAs the factor of intertrial duration, which unsurprisingly cast a hefty effect. The shorter the trial, the longer the RT. Here are some figures at last. We found that both change magnitude and change direction affected the response times. As to change magnitude, shown in these figures in blue shades, shorter RTs were yielded to larger steps. The effect was very robust. A smaller, but still significant effect was seen for change direction, shown here in magenta and purple, with shorter RTs yielded to melodic fall versus rise. Absolute frequency also cast an effect, shown in red shades. The higher the tone, the shorter RT, but several comparisons enabled us to tease the effect of absolute frequency apart from that of change direction. The muscle data revealed an astonishing mean work onset latency at about 68 milliseconds post-trial onset. This is when mean activity exceeded the baseline confidence intervals. Very early indeed, when you think about the time needed for the motor command to travel from brain to muscle. And there were more intriguing results ahead. We ran the same ANOVAs on the muscle data as we did on reaction times. The effect of change magnitude and change direction were similar to the effects found in RT. Change magnitude shed stronger and earlier effects than change direction. Remarkably, as you can see on this slide in the blue shades, the effect of change magnitude was robust and statistically significant from the first milliseconds following muscle work onset. Already there, response to bigger steps preceded that to single steps. Finger acceleration results corroborated the EMG results. We recorded the brainstem response, namely wave 5, and the following components up to N100. First, we examined the brain activity evoked by new frequency per se. We analyzed the mid-tone only, comparing responses to new frequency at trial onset versus responses to the following mid-tone filler beeps, which presented no frequency change. The figures on the right show activity along the auditory pathway. New frequency in pinkish purple and filler beeps in gray. The ERP data revealed that new frequency elicited enhanced peaks already at brainstem, and then through the following components as well. As shown here, effect sizes spanned between moderate and large. Frequency change also elicited enhanced mean amplitude from component NA on, and earlier peak latencies at component NA and NB. Previous evidence from the last decade did show detection of frequency-related changes in the middle latency responses, but to our knowledge, our study is the first to show detection of frequency change in pure tones at the human brainstem within 10 milliseconds from stimulus onset. 1 second. As for detection of frequency change type, we found effects of change magnitude and change direction on the different ERP components. Also here, the effects commenced already at the brainstem. Regarding change magnitude, at the brainstem, bigger steps yielded more enhanced wave 5 peak amplitudes than single steps. This effect was small, but statistically significant. Regarding change direction, at the brainstem, rise yielded earlier wave 5 peaks than fall, a medium effect. And rise also yielded lower mean amplitude than fall. So it is not only that frequency change per se was detected at brainstem, its magnitude and direction were discerned that early as well. Both parameters were also reflected distinctly in later components, from NA to N100. Having analyzed these telling behavioral data, muscle data, and brain data, we ask now in which level of auditory processing could a motor command have been issued? Because the effect of change magnitude was our stronger behavioral effect, we searched for correlations within subjects between muscle work onset latencies at circa 70 milliseconds post sound onset to single versus double steps, and the peak latencies of the preceding ERP components to these cases. We found significant correlations with EMG onset latency of both the NA and PA peak latencies. Though we were not able to measure directly neural transmission time between brain and muscle, an estimation of circa 35 milliseconds supports the correlations I mentioned, which involve ERP peak latencies at circa 30 to 35 milliseconds post-sound onset and EMG onset at 70 milliseconds. Within the ascending auditory pathways, the NA component probably originates in the thalamic level of processing, and the PA in thalamocortical pathways or very early stations in the auditory cortex. This may fall in line with findings as those of Guillory, who showed that a portion of the axons ascending into the thalamus bifurcate, with the non-thalamic end going back to motor output centers in the brain and spinal cord. Guillory also suggests that messages which thereafter travel from thalamus to A1 include both the sensory information and information on evoked motor actions. So we are excited about these intriguing, suggestive results and the possible route they hint at. The last brain issue we wanted to address was the frequency following response, FFR, because previous research found that FFR strength predicted RTs. In analyzing the FFR elicited by a new frequency, we focused again on the mid-tone only, because FFR is frequency dependent. Our FFR does have two limitations. First, a priori, our design, which was well tailored to fit many demands, was not perfect for FFR investigation. We had only 660 cases of first beeps at mid-tone per subject, which is 1/3 of the standard number for trials for FFR analysis. About the other limitation we found only in the data analysis process. It turned out, annoyingly, that the standard biosemi MK2 model, which we used for EEG acquisition, contaminates the data regularly with a byproduct of 8 Hertz and all its multiples up to well beyond the FFR range, a fact which biosemi does not publicize. Still, we do have important FFR observations to report. On this slide, FFR strength is reflected by the pairwise phase consistency between all trials. The x-axis is time in milliseconds. And sound onset and offset are marked by vertical lines. We compared responses to mid-tone first beeps at trial onsets, shown here in blue, to those at the filler beeps which followed. First beeps exhibited an initial peak right after wave 5, followed by a lesser plateau despite the ongoing sound. In contrast, at filler beeps 1 and 2, here in yellow and green, where the frequency percept was more established, strong FFR was maintained until the beeps end and even later as an after effect. Filler beeps 3, 4, and 5 exhibited adaptation. On the second FFR figure, the y-axis represents frequency, and the horizontal red line is at the expected oscillation. We found honing into the frequency and an after effect following the tone, as found last year also by the group of Zatorre. However, statistical power did not suffice to compare within arrivals to the mid-tone, rise versus fall, and single versus bigger steps, because each of them had only 330 cases. To summarize, we found ultra-rapid motor responses to frequency change, affected by change magnitude and direction. Responses were faster to larger changes, consistent with previous literature. They were faster to melodic fall, somewhat surprising, also considering our own previous stepping studies. Perhaps our stressful task led our subjects to what Niemi and Nettanen termed in 1981 an aversive state, which rendered falling frequency to be perceived as alarming, as in the animal kingdom, where falling auditory contours connote threat and danger. These super-fast responses were enabled by detailed detection of change already at brainstem and in the components immediately following. These novel findings extend previous work, showing that in very early levels of the auditory pathway, neurons respond not only by stimulus features, but by stimulus history, a kind of working memory. Our results point to very early stations in the primary auditory cortex, or perhaps even beforehand, at the vicinity of the thalamus, as possible relay hubs from auditory input into motor output. Intriguingly, this early junction seems to host some form of decision capacity, normally associated with much later and higher levels of processing. Could our motor system be perpetually but covertly engaged by auditory input? Could there exist a low-level motoric facet of melody perception in music? Embodied music perception in a very literal sense. When our auditory system detects a frequency change, is our perception of it affected by the motoric ripples it steers? And this sums up my talk. And I would just like to add that it is really basic questions in what music is that are behind all of this. I mean, my study was very concrete for a very specific question, but I think maybe responses to music are imbued with this quality of responses to whatever auditory things we hear and our behavioral responses to them. So I hope this will steer a discussion in this or other directions. All right. Thank you.
All right. Thanks so much, Amos, for this very detailed and really super interesting result. I think I'm going to move over to see that some questions have arisen. Thank you, first of all, again, for this very interesting talk. I do have one question already for you from Daniela Samler. She says, yes. Fascinating. You found fast response times for melodic faults. Could this be related to the direction of the finger movement, button press downward, stimulus response are compatible?
Yeah, compatibility, yes, the yes. Stimulus response compatibility. Yes, so this is one of the caveats I mentioned in the paper which we are about to publish. But I do not really think so. First of all, the finger movement was very, very small. And secondly, these were expert musicians that were taking part. And also on the instruments they play, depending on the instrument, movement of the finger downwards can result sometimes in the sound going upwards, depending on the instrument. For example, I play viola, so when I press my finger down on the string, the sound is turning higher. So, so I think if it had any effect, it's very small. And also in our tapping studies, actually, the finger also went down, and there the rising direction was earlier. So. But these were, as I said, in this experiment, it was very tight and very stressing condition for the participants. And in the tapping studies, it was not. So maybe this were, I think, this difference might arise from these conditions and not from the stimulus response compatibility. But okay. definitely, I did think. I think if we would have done a response button pressing upwards with the finger for response, it would have been, I think, very artificial, and I'm not sure if it would balance the result.
Mm-hmm. This would have been Daniela's next question, but you give an answer to it already. So
I didn't see it. I see only the screen of the PowerPoint, and
that's why I'm reading this out for you. So
thank you.
Okay, we have another question by Nathaniel Zuck. Why did you choose to work with experienced musicians for this study? Did you also study people without musical experience?
Yeah. So. I wanted very much to test both groups, and this experiment took a lot of time. And the next experiment I would very much like to do would be exactly with non-musicians, especially that in our tapping studies we had non-musicians and musicians, and actually non-musicians responded more. With more discerned responses to these changes of parameters, because musicians were very disciplined, so they didn't alter the tapping, and this was in the tapping task world. But now this is in the reaction time task world, and I was very curious to see what's going to be with non-musicians. And I'm sure we are going to have important insights from testing non-musicians, because musicians are like experts, and it has been known in the literature that experts in different tasks, not only in music, like for typists and also for sprinters, they tend to use for their motoric acts like shortcuts in their neural roots through the reticular formation, and routes like this, which might be a privileged access for experts, or myelinated neural roots. So I'm very much expecting to do a follow-up experiment in non-musicians, and thanks to Nathaniel. Yeah.
So I was also thinking about other types of non-experts, though, like gamers, for example, who use a lot of finger-related movement and rely on sound feedback. And so the question is indeed, what type of expertise does it take to gain these results? And it is likely not necessarily something that is entirely related to musical expertise.
Right. Thank you very much. Yeah, I agree totally. Yes, we should do it. Yeah. So far, we only did the musicians, and yeah, we should definitely continue to other groups, and I'm sure there will be insights.
All right. Well, Amos, thanks again for these really intriguing data and sharing them with us. Very much appreciate your presence today.
Thank you.